Yes, sir. Yes, sir.
So I hope my screen is also visible in the full screen mode.
Yes, sir.
Yeah, thank you. So let us start the session. So in today's session, we're going to see the regression analysis. So if you remember, we had discussed the three types of learning paradigms. One is supervised learning, unsupervised learning, and reinforcement learning. So in the supervised learning, we said there are two problems: regression problem and the classification problem. So we're going to discuss the regression problem today and one of the solution for the regression problem, which is the linear regression, and also the optimization behind this solution also we will see, and we'll also look at the probabilistic interpretation of this cost function. So this is what is the agenda for today's session. So we'll be seeing what is the problem and solution for it, linear regression model. Then we'll be looking at the optimization part of it. We're going to discuss various algorithms, including gradient descent algorithm, mini batch gradient descent algorithm, stochastic gradient descent algorithm, etc. We'll also see the vectorization part of it, closed form solution as well, some of the practical advices while implementing this algorithm, and also we will see the probabilistic interpretation of the linear regression. So this is the agenda for today. Okay, so we'll start with the problem. So do you remember what is the regression problem? Can anyone tell me what is the regression problem? Regression problem. Do you remember regression problem? Classification, regression problems we had discussed, right? What is the difference between them? Regression and the classification problems?
Linearly separable.
Linearly separable. No, I'm just asking the difference between the regression and the classification problems. If the target variable is continuous,
Yeah.
we call that problem as a, what is that? Regression, right? So if the target variable is discrete, then we call the problem as a classification problem, isn't it? Yeah. So the house price prediction problem, does it comes under the regression problem or the classification problem? Regression problem, right? Identifying to which folder an email should belong to. This comes under classification problem. Yeah. So now you remember, right? So this is the problem. We have given the training set of pace. So the training, very simple problem, not much here. So we have given a training set of pace x1, y1, x2, y2, so on xm, ym. Here xi is a d-dimensional feature vector and yi is a continuous target variable, right? And given this data set of m instances of input output pairs, and given a new instance for which we only know the input vector, but we don't know what is the corresponding target value is, right? And the task is to predict this problem. So this is what is the regression problem is. So we have given the training set of pairs x1, y1, x2, y2, so on xm, ym, where xi is the d-dimensional feature vector and yi is the continuous target variable. So the task is to predict for the new instances xm plus j for j greater than or equal to 1. So very simple problem. Okay. So now we'll start with the example to understand this better. So here is the house price prediction example. How do we predict the housing prices? So we collect the data regarding the housing prices and we analyze how they're related to size in square feet. So for simplicity, here it is taken only one input feature, which is size in square feet, and the target variable is the price in dollars. And these are the various houses distributed in the two-dimensional space according to their size and price, right? So given this data set and given that a friend has a house of 750 square feet, how much can they be expected to get? Okay, so this is what the problem that we are trying to solve precisely. We have given the data of M houses, given a new house for which we only know the size of the house, but we don't know what is the price of the house. The task is to predict the price of the house for this new house for which we only know the size of the house as the 750 square feet. Okay, so what we do, we analyze how this size in square feet is related to the price of the house. Okay, suppose if I model the relation as a straight line as you see in the first figure, right? It means if I'm trying to capture the underlying pattern of the data through this straight line, if I'm trying to fit this straight line to the data, or if I'm trying to model the pattern of the data as a straight line, then for 750 square feet, it would be around $150,000. Am I right? So 750 will be somewhere here. According to this line, prediction would be somewhere here, which is $150,000. So if I try to model this as some curve in the second order polynomial curve, as you see in this figure, right? It means if the underlying pattern is captured through some curve, second order polynomial or third order polynomial, in this case it is a second order polynomial, for 750 square feet, how much can they be expected to get according to this underlying model, or the model that it is trying to fit for the data? It would be around $200,000, right? So the prediction, depending on what model that we employ or how you model this data, right? How you capture the underlying pattern of the data, right? So that depends on the assumptions that you make about the data. Suppose if you assume that the data is linear, it means the relation between output and the input variables is linear, then we may go for the line or a hyperplane. So if you assume the relation is non-linear, we may go for the second order polynomial or third order polynomial and so on, nth order polynomial. So what kind of model that we employ is depending on the assumptions that we make about the data. So we'll start with the linear assumptions. It means we assume initially that there exists a linear relation between input and the output variable. Then we will go for the non-linear models later. Okay. So far, are you with me? I hope you're following it.
Yes.
Yes, sir.
Yes. Okay. Yes. So let us start with the linear regression model. This assumes that there exists a linear relation between input and the output variables. It means it assumes that the output is a linear combination of the input variables. Okay, it means it assumes that the relation between the target variable and the features or the input variables can be modeled through a line or a hyperplane. That's what the assumption is in case of linear regression model. So before we're going to discuss the linear regression model, let us try to understand the general machine learning recipe for the supervised learning problems. So the general machine learning recipe for the supervised learning problems is like this. We are given a training data that is input output pairs of M instances. So the training data is passed to the learning algorithm. The training data is given to the learning algorithm, and learning algorithm gives us some hypothesis. We also call it as a model. We also call it as a function. We also call it as a pattern. There are many names for this. So once you give the training data, learning algorithm captures the pattern of the data and it gives us the hypothesis. And we use this hypothesis to make a prediction for the future instances. In this example, given the size of the house to the hypothesis, it will be able to estimate the price of the house. So this is the general machine learning recipe for the supervised learning problems. Training data is given to the learning algorithm, and learning algorithm gives us the hypothesis or a model, right? And given this, once we get the hypothesis, we make use of this hypothesis to make a prediction for the future instances, right? Now, the representation of the hypothesis depending on the model that we select. Okay, so what is the representation of the hypothesis in case of linear regression model is the next question that we are getting here, right? So what is the representation of the hypothesis? So it is the representation of the hypothesis based on the assumptions that we make about the data. Here the assumptions are there exists a linear relation between input and the output variable. It means it is assuming that output is a linear combination of the input variables. It is assuming that the output is a linear combination of the input variables. In simple words, it is trying to fit a line or a hyperplane to the data. All right. So yeah, so this is what is the supervised, general machine learning recipe for the supervised learning problems. We are giving a training set to the learning algorithm. Learning algorithm is giving us the hypothesis. We use this hypothesis to make a prediction for the future instances. And the representation of the hypothesis in case of linear regression model is a line or a hyperplane. Line in the two-dimensional space, hyperplane in the multi-dimensional space. So can you tell me what is line? What is the line equation? Can you tell me what is line equation?
Y is equal to
plus C.
mx
Y
plus
equal
c.
to mx plus c, right? So this is the
Y
representation
equals
of,
to mx plus c.
yes, great. So y equivalent to mx plus c is the representation of the hypothesis here. You look at this hypothesis representation here. Isn't it looking like a line? H theta of x equivalent to theta naught plus theta 1 x. The same, right? Where theta naught equivalent to c and theta 1 equivalent to m. Am I right? So here, theta naught and theta 1 are the parameters of the model, right? So a linear regression with one input variable, we call it as a univariate linear regression. And a linear regression with multiple input variables, we call it as a multivariate linear regression. So first we will explore univariate linear regression, then we will move to the multivariate linear regression. So in the univariate linear regression, we have only one input variable and one output variable, right? One input variable and one output variable. Fine. So now I said that we are trying to represent the hypothesis as a line or a hyperplane. It means we are trying to fit a line to the data, isn't it? So now if you take the data, there are many lines that goes through the data. You see that this line goes through the data, this line goes through the data, this line, 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 this line. The infinite number of possibilities, all of them are going through the data, right? So which is the best line out of all these infinite number of possibilities that we have is the question, is the next question that is coming in here. So far we said that we are trying to fit a line to the data by using the linear regression model. But which line? There are many lines. You take that there are infinite number of lines that are going through this data. So which is the best line out of all these infinite number of possibilities that we have is the question, right? So let me give you a different problem, slightly different problem, and try to answer to this question. So let's say that there are some group of houses. Let's say that the group of houses are arranged something like this, as it is shown in this figure, right? Something like this, right? These are the group of houses. Okay, you're an engineer, you're asked to lay a common pipeline to this houses so that you can give a water connection to the individual houses. So which direction would you prefer? Which direction would you prefer to lay a common pipeline? I give you two options. One is this one, direction 1. The other one is this direction, direction D2. Which direction would you prefer to lay a common pipeline?
D1.
D1, sir.
You prefer D1. Why is it so?
They are aligned.
Yeah. Actually, please let me check my audio. I could hear voices are very low for me. I couldn't hear. Give me a second. It's complete. Yeah. Now can you answer?
Sir,
Which
they are
direction?
aligned.
D1.
In D1.
D1. Why is it so?
It is closer to all the houses.
It is closer to most of the houses. Okay, it means that if I lay a common pipeline in this direction D1, then cost will reduce. Am I right? Because the distance between the common pipeline and the individual points is lesser in this case of direction D1, whereas the distance between the common pipeline and the individual houses is more in case of D2. It means the cost will be more if I if I lay a common pipeline in the direction of D2. Am I right? Hello? Is that right? Is that the reason that you said D1? Yes. So now let me give you points. These are the points in the two-dimensional space. I just want you to fit a line so that you can capture the pattern of the data. So which direction would you choose? Which line would you choose? Line 1 or line 2?
Line 1.
Line 1, sir.
Line 1.
Line 1 we choose. Why is it? Because if you choose line
Because
1,
most of the points
are
close to line 1.
It means
Line 1.
the difference between actual and the predicted values is minimized if you choose line 1, whereas the difference between actual and the predicted values is more in case of line 2. Am I right?
Yes.
Is that yes? So what is that we are trying to do here? We're trying to minimize the difference between actual and the predicted values. So can I say the line that minimizes the difference between actual and the predicted values is the best line out of all the infinite number of possibilities that I have? Can I say that?
Sir. Yes, sir.
Right.
Yes.
So
Yes.
the line that minimizes the difference between actual and the predicted values is the best line out of all these possibilities. But what makes one line different from the other line? Let's take two lines, 2x plus 3 and 3x plus 4. And the general representation of the line is theta naught plus theta 1 x, right? So what is making this line different from this line? The two parameters, theta naught and theta 1. Am I right? This is what is making one line different from the other line. So what do we mean by choosing the best line? Choosing the best line is equivalent to choosing the best parameters, theta naught and theta 1. Isn't it so? Hello? Isn't it so? Choosing
Yes, sir.
the best line is equivalent to choosing the best parameters theta naught and theta 1. So the problem is boiling down to choosing the parameters theta naught and theta 1 so that the prediction h theta of x is close to the actual value y for all the training examples. So this is what is our objective. Our objective is to choose these parameters theta naught and theta 1 so that the difference between predicted value h theta of x and the actual value y is minimized for all the training examples. So that is what is our objective. So is the objective clear to all of you? Is the objective clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So we'll try to formulate this objective in the mathematical notation. So here is our objective. We want to choose theta naught and theta 1 such that the loss function j of theta is minimized. And what is the loss function? 1 by 2m sum over I equal to 1 to m h theta of xi minus yi. Here we are taking the squared loss. H theta of xi is the predicted value, yi is the actual value. So we want to minimize the squared difference between actual and the predicted values for all the training examples. And this 1 by m is to take the average, 1 by 2 is to simplify some future mathematics. And it is not violating our objective because minimizing some function f of x is equivalent to minimizing f of x by 2. So this is not violating our objective. At the same time, it is simplifying some mathematics. So that's why we just kept 1 by 2 in the denominator there. So the objective is now to choose theta naught theta 1 so that the squared difference between actual and the predicted values is minimized for all the training examples. So why squared loss? Why squared loss? There is some theoretical intuition behind that. There is some probabilistic interpretation behind that. So that we're going to see at the end of this session. But let us just try to understand some intuition behind this squared loss. So usually the intuition behind any loss function is that the more the prediction is deviating from the actual value, the more penalty we add to the cost function. And the objective is to minimize the overall loss. So let us take an example to understand this better. So let us take the predicted value actual value y and predicted value h theta of x. And also the loss that it is adding in each of these cases, h theta of xi minus yi whole square. Okay, 1 by 2 also there. You can ignore that as it is a constant. Fine. So suppose if the predicted value is 1, actual value is also 1. Actual value 1, predicted value is also 1. So how much penalty we should add to the cost function if the predicted is equivalent to the actual? we need not add any penalty, isn't it so? Because we are getting whatever is expected, isn't it? So absolutely whatever is expected, that is what the system is predicting. So why to add a penalty? You need not add any penalty, isn't it? Hello?
Yes, sir.
So we add a zero penalty in this case, right? So x theta of xi minus yi. So let me write it with to avoid confusion. We add a zero penalty in this case. 1 minus 1 whole square, zero penalty. Suppose if the predicted value is 2, actual value is 1. How much penalty we are adding in this case using the squared laws?
Sir, 1.
1 penalty. If h theta of x is 3, predicted value is 3, actual value is 1. How much penalty we are adding?
Sir, 4.
4. If the predicted value is 4, actual value is 1, then
Sir, 9.
9. This is 5, this is 1. Then you add a penalty of
16.
16. So what is your observation? The more the prediction is deviating from the actual value, the more penalty you are adding to the cost function. That's the intuition behind the squared laws. So of course it has some disadvantage also, that it is like penalizing the outlier points more, and that way it is trying to fit the outlier points into the model, and that way it leads to the overfitting also sometimes. But this is the intuition behind this. Okay. But there is some theoretical intuition also. There is some theoretical background for this also from the probability concepts point of view. That also we'll see later. But this is the simple intuition behind this squared loss function. The more the prediction is deviating from the actual value, the more penalty we are adding to the cost function. All right. Now, the objective is to choose this theta naught and theta 1 so that the squared difference between actual and the predicted values is minimized. Now the question is how to achieve this? How can I choose the best theta naught and theta 1 that minimizes the squared difference between actual and the predicted values is the question. So how can I choose the best theta naught and theta 1 that minimizes the squared difference between actual and the predicted values is the question now. So is it okay if I do this? I'll be chanting some mantra, Om Haim Kleem, and I'll be selecting this theta naught and theta 1. I would say that this is the best theta naught and theta 1. Right? Would you agree with me?
Yes, sir.
You will agree that by chanting mantra, if I get theta naught and theta 1, that is
No,
the
sir.
best.
No.
Definitely you cannot agree to me, right? Randomly chosen theta naught and theta 1 can't be the best theta naught and theta 1. By chanting mantra or without chanting mantra, whatever it is, the randomly choosing theta naught and theta 1 cannot be the best theta naught and theta 1, isn't it? So you have to learn the optimal parameters gradually by initializing them to some random values, right? So how to achieve this is the question. So that is where exactly the gradient descent algorithm helps us. Gradient descent algorithm is a kind of optimization algorithm that learns the optimal parameters of the model that minimizes the loss function, right? Gradient descent is an optimization algorithm that learns the optimal parameters of the model by minimizing the loss function. So it chooses the parameters theta naught and theta 1 that minimizes the loss function. So before we're going to discuss what is gradient descent algorithm, let us try to understand what is a gradient. What is gradient? So by the way, could you follow? Are you with me so far?
Yes,
Before
sir.
we move on.
Yes, sir.
Yes,
Yeah.
sir.
Thank you.
Sir, yes,
So
sir.
before we move on to this gradient, let us try to understand a gradient descent. Let us try to understand what is gradient. Okay. So you all know what is gradient. Let us try to recollect that. Just recollect that. So what is gradient? So to understand this concept of the gradient, I've taken a very simple function, which is the line equation, y equivalent to mx plus d. Let us try to interpret different variables that we have in this function, y equivalent to mx plus d. So what is y? What information that y is giving? How far this line is up, isn't it? So y is giving how far this line is up, x is giving how far this line is long, and m is the slope of the line. We also call it as a gradient. So which is giving the information about the slope of the line, right? And b is the value of y when x equivalent to 0, right? Which we also call it as an intercept, right? So here we are interested in knowing what is the gradient, what is the interpretation or what information that this gradient is giving us, which is m, which is indicated with this m, right? So what information that m is giving? M is giving how steep the line is, or what is the slope of the line, or what is the gradient of the line. It means we want to know how y is varying as you vary x. It means as you vary x, what is the slope of this line y? That's what the information that we want. That is what the gradient is giving us. So if you want to know how this line slope is varying as you vary x, it means is the line is ascent, or is the line is descent, or is the line is going straight. This is what the information that is m is giving. So if m is positive, then the line will be like ascent line. If m is negative, line will be descent. If m equivalent to 0, line will be horizontal, as you see in this figure, isn't it? So that's what the information that m is giving. So if the line is something like this, then m will be negative. If the line is something like this, m is positive. If the line is going straight, like a horizontal line, then it is axis parallel line, then m equivalent to 0, right? So this is what the information that m is giving. So I just want to know what is the slope of this line as I vary x. It means I just want to know the slope of this line mx plus d as I vary x, right? So is it a positive or is it a negative? What it is actually, that we can get through this m value. So if you want to know slope of some function with respect to some variable as you vary that variable, then we have to take the partial derivative of that function with respect to that variable. Partial derivative of y with respect to x. So what would you get when you take the partial derivative of mx plus b with respect to x? What will you get?
M.
M.
You will get m, which is nothing but the slope or the gradient. So if you want to know the slope of some function with respect to some variable, take the partial derivative of that function with respect to that variable. And if your function is a function of multiple variables, let's say that it is x1, x2, so on, right? Function of multiple variables. You can take the partial derivative with respect to multiple variables, and vector of all such partial derivatives will give you the gradient. So the gradient is just a vector of the partial derivatives. Since the concept of the gradient is clear and how to compute the gradient is also clear, these 2 points from this slide.
Yes, sir.
Right. So if you want to know the gradient of a particular function with respect to one variable, then take the partial derivative of that function with respect to that variable. So now let us move back to our problem. What is our problem? Our problem is to choose this theta naught and theta 1, two parameters of the model, so that the squared difference between actual and the predicted values is minimized. So when I plot this cost function versus one of the parameter theta 1, it looks something like this: convex optimization problem, as you see in this figure. And what is our objective? Our objective is to choose theta 1 that minimizes this j of theta. So according to this, what is the optimal theta 1? The optimal theta 1 is the theta 1 corresponding to the lowest value of this j of theta. Am I right? It means this is the optimal point. The theta 1 star is this. So we are interested in learning this theta 1, which is where j of theta is minimum. Hello, am I right? We are interested in learning this
Sir.
point only, right? Right. But when I randomly initialize, this theta 1 can be anywhere. Need not be there only, right? The theta 1 can be here, the theta 1 can be here, it can be anywhere, because you're just randomly initializing it. Okay. So we randomly initialize it, but gradually we have to move to this optimal point. Okay. So how can I do that? How can I gradually move to the optimal point is the question now, right? So let's say when you randomly initialize, the point is somewhere here. Let's say when you randomly initialize, the point is somewhere here. So what is the slope of the function here? Is it a positive or a negative slope? Is it a positive slope or a negative slope?
Negative slope.
Negative slope, right? If that is like this, then it is a positive, but here it is like something like this. So the slope of the function is negative here. So right now you are here, you want to go to here. It means your current theta is this, your optimal theta is this. Theta star is this, the current theta is this. Current theta 1 is this, optimal theta 1 is this. So do you have to increment or decrement to reach to the optimal point? Do I have to increment theta 1 or decrement theta 1 to reach to the optimal point?
Increment.
We have to increment, right? We have to increment, we have to increase theta 1 to reach to the optimal point, right? So let us take another scenario. So let us take when you randomly initialize, theta 1 is somewhere here. What is the slope of the function here? Is it a positive slope or a negative slope?
Positive.
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 This is a positive slope. So your current theta 1 is this and the optimal theta 1 is this. So current theta 1 is this, optimal theta 1 is this, here somewhere, right? So do I have to increment or decrement to reach to the optimal point?
Decrement.
Decrement.
Decrement. So it means what? When the slope is negative, we have to increment to reach to the optimal point. When the slope is positive, we have to decrement theta 1 to reach to the optimal value of this j of theta, right? So is that okay if I do that? Is this algorithm looks fine? Looks fine, right? It means I compute the gradient with respect to theta 1, and if this gradient or if this slope is positive, I'll decrement theta 1 to reach to the optimal point. If this gradient or the slope is negative, we have to increment theta 1 to reach to the optimal point. Is that looks fine so far?
Yes.
Right.
Yes.
So, but how do you compute the slope of this function j of theta with respect to theta 1? How do you compute slope of this j of theta with respect to theta 1? It means I just want to know what is the slope of j of theta as I vary theta 1. How do you get that?
Derivative.
Take the partial derivative of j of
Slope.
theta with respect to what? Theta 1. That's what we said right here. If you want to know the slope of y with respect to x, you took the partial derivative of this line with respect to x. Here you want to know the slope of j of theta with respect to theta 1. So what we have to do? We take the partial derivative of j of theta with respect to theta 1. Similarly, if I want to know the partial slope of the function with respect to theta naught, then what should I do? Slope of this j of theta or the cost function with respect to theta naught. What should I do?
Derivative with respect to theta naught.
Derivative of j of theta with respect to theta naught.
Theta naught.
Yes. All right. So now, just for the simplicity, we have shown in the two-dimensional space with only one parameter. What if you have multiple parameters? Like this function itself, there are two parameters of the model, not just one parameter. So this function can be visualized like a ball in the multi-dimensional space. Okay, so this is like a ball in the multi-dimensional space, and our objective is to reach to this bottom of the ball where j of theta is minimum. It means you'll be initializing two parameters theta naught and theta 1 randomly. Let's say when you randomly initialize, it is somewhere here. So you have to gradually adjust both theta naught and theta 1 such that you reach to this optimal point. Okay, so that is what is the objective. So one more point that I would like to mention here. Tell me, what do you see when you see this from the top view? What do you see when you see this three-dimensional figure from the top view? Top view. What do you see when you see the ball from the top view?
A plane-like structure.
Like concentric circles, right? Something like
Yeah.
this.
Yes. Yes, like this.
Something like this. And this is the two-dimensional representation of this
Plane-like.
function. Yeah, this something like this. Theta naught and theta 1. And our objective is to reach to this middle point. So when you randomly initialize, it may be somewhere here. You may be gradually adjusting them and reaching to this optimal point. So this we call it as a contour graph. Contour graph. We're going to use this concept in the coming slides. That's why I'm demonstrating it here. This we call it as a contour graph. All right. So far, is this clear?
Sir, can that graph become concave?
Concave. If it is a maximization problem, then it is a concave. This is a minimization problem, right?
Yes.
If it is a there are some maximization problems also. then it's like the concave. Then the objective is to reach to the peak point of this graph. So then we use a gradient ascent algorithm. Here we are using the gradient descent algorithm, right? There it is a
Yes,
gradient
sir.
ascent algorithm.
Yes, sir.
All right. So, all right, we have got some tentative algorithm. Let us try to finalize that. Is this okay if I do this? I initialize theta naught and theta 1 and repeat the following process until convergence. So, following process means we are up theta j equivalent to theta j minus some alpha times the derivative of j with respect to theta j for j equivalent to 0 and 1, right? So, what is this is giving? Derivative of j with respect to theta j, what it is giving? Isn't it the slope?
Yes.
Isn't it the slope? Right?
Yes.
This is the slope. So when
Yes.
the slope is positive, what we have to do? Decrement or increment?
Minus.
Increment.
Decrement. The
Decrement.
slope is negative, we have to
Increment.
Increment.
Okay. So if this is positive, what are you doing? Ignore alpha for some time. Let's take it as alpha equivalent to 1. So theta j equivalent to theta j minus some positive quantity. What is that, decrement or increment? Theta j equivalent to theta j minus some positive quantity. Are you decrementing or incrementing?
Decrementing.
Decrementing only, right? You are subtracting some positive quantity. It means you're decrementing it, right? If this is negative, then minus of minus, it will be positive. Are you decrementing or incrementing? Incrementing. It means what? When this is positive, you are decrementing theta j. When this is negative, we are incrementing theta j. That's what we wanted, right? When the slope is positive, we have to decrement. When the slope is negative, we have to increment. That is what we wanted. So is this okay if I do this? This looks fine, isn't it? Hello? This looks fine. The algorithm looks fine. This we call it as a gradient descent algorithm. We call it as a gradient descent algorithm. It decrements the theta j or the parameters when the slope is positive, increments the parameter when the slope is negative. All right. Coming to this alpha. Alpha we call it as a learning rate or the step size. Okay. So which determines the step size that we are taking. It means if the alpha value is big, then we may be taking bigger steps to reach to the minimum value of z of theta. If the alpha value is smaller, we may be taking tiny steps, smaller steps to reach to the optimal value of z of theta. We'll discuss this later. We have one more slide on this. So we'll discuss about this. What step size should we choose? We'll discuss it later. Okay, but this is the step size or the learning rate, we call it as. All right. So now let us try to take the derivative of the cost function with respect to theta naught and theta 1. It is directly given here, but let me also derive it, right? So all of you are good at gradients, right? Derivatives, right? I'm assuming that. Can you tell me what is the cost function? Do you remember that? Cost function, the squared loss function.
1 upon
1 upon
2m.
2m summation of
equal to 1 to m
predicted minus actual bracket square.
minus y whole square.
So this is what is the objective function, right? Very nice. Can you tell me the representation of the hypothesis h theta of xi? Theta naught plus theta 1 xi. Am I right? Representation of the hypothesis is a line only, right? Theta naught plus theta 1 xi. Yeah. Now you're taking the derivative of z of theta with respect to theta naught, let's say. So when you take the derivative of z of theta with respect to theta naught, you can expand this also. Let us expand this. So this is equivalent to 1 by 2m sum over I equal to 1 to m theta naught plus theta 1 xi minus yi whole square. So this is j. You tend to take the derivative of j with respect to theta naught. What will you get? This 2 will come this side, isn't it? Hello? When you take the derivative of this 2 will come this side. Am I right? 2 will come this side. Now you might have understood why we have taken 2 in the denominator. To get it cancelled with this, we have taken this 2 in the denominator to simplify this mathematics. So sum over I equal to 1 to m theta naught plus theta 1 xi minus yi times derivative of this again, which is equivalent to 1, because rest of else it is 0. I can show you also derivative of theta naught with respect to theta naught plus derivative of theta 1 xi with respect to theta naught, which is 0, and derivative of yi with respect to theta naught, this is also 0, and this is 1. Am I right? Hello? Could you follow?
Yes, sir.
Yeah, I mean, you need not, even if you don't follow, that's okay. You, as long as you understand that derivative of with respect to theta naught is this only. Okay. I'm just trying to derive so that it is better for you, that you will not have any confusion later. So this is 1. So isn't it this 1 by m sum over I equal to 1 to m h theta of xi minus yi? This one. Hello? Following? Where is
Yes,
Deepa
sir.
madam is not
Yes,
there
sir.
today.
Yes, sir.
Is she there, Deepa madam? I think she's not there today. All
Yes,
right.
sir, I am there, but I can't attend properly today.
Okay. Any query you can ask madam.
Sir, actually, there is a lot of disturbance from where I'm attending. I'm in marriage, sir.
Okay. Oh, from that's great. Marriage also that. No problem, ma'am. Please go through the video later. Okay. And ask me if you have any queries in the next class.
It is very, very important session and I'm really feeling very bad, sir.
Don't worry. You can go through the video and ask me if you have any queries. Fine. So is it clear to everybody else? Madams and sirs?
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir.
Yeah. Thank you. So now similarly, can you take the derivative of z with respect to theta 1? This would be the same, but here instead of 1, what will you get? When you with respect to theta 1, you will get xi, isn't it? So this is xi. Hello, should I derive it? This 2 coming this side, 2 and 2 get cancelled, and derivative of this with respect to xi, right? Which means derivative of theta naught with respect to xi, which is 0, and plus derivative of theta 1 xi with respect to xi, which is, sorry, with respect to theta 1, I'm sorry, theta 1. Okay, this is xi, and derivative of y with respect to theta 1, which is also 0, right? So finally you got xi here, which is this. Okay, I think this is clear. Shall we move on? It is clear. Otherwise, if you want me to repeat something, I can do that quickly. Clear?
Yes, sir.
Yes. Okay, thank you. So the gradient descent is an optimization algorithm which is used to find the optimal values that minimizes the cost function, optimal parameters that minimizes the cost function. That is all about the univariate linear regression. So univariate linear regression means only one input variable and one output variable. Now we'll move to the multivariate linear regression, wherein we have multiple input variables. So if you see this price of the house, not just the size of the house, there are many other factors that influences the price of the house. Like for example, what is the number of bedrooms, number of floors, what is the age of the house, what is the size of the garden. All these are the various features that influences the price of the house. So considering more features will influence the prediction quality, right? So it means it improves the performance of the model, right? So here we have considered multiple input features or input variables. Like four features we have taken: size of the house, number of bedrooms, number of floors, and age of the house. Okay, here are some of the notations that we follow. X superscript I is the d-dimensional feature vector. Like for example, if I say X superscript 3, this is the feature vector corresponding to the third house, which is this. Okay, and subscript we use for the denotion, we use it to denote the feature value or the attribute value. For example, X superscript 3 subscript 2, which means the number of bedrooms in the third house, which is this number of bedrooms in the third house. And yi, you know, which is the corresponding target variable, right? So it means y3, if I give, this is the price of the house here, right? So is the notation clear? Shall we move to the next slide if the notation is clear?
Yes, sir.
Notation, yes. So previously, in case of univariate linear regression, our hypothesis representation is just a line, right? It means the representation hypothesis is theta naught plus theta 1 x. So now we have got multiple features, x1, x2, so on, xn, where n is the number of features, right? Now the representation of the hypothesis is a hyperplane. Theta naught plus theta 1 x1 plus theta 2 x2 plus so on theta n xn. So this is what is the representation of the hypothesis in case of multivariate linear regression. So to generalize this, I can take x naught equivalent to 0 and write it this way: theta naught x naught plus theta 1 x1 plus so on theta n xn. I can even give the vectorized notation of this by taking the vectors like theta equivalent to a vector of all the theta values, theta naught, theta 1, so on, theta n, and x I can take it as a vector of all these feature vectors, right? X naught, which is equivalent to 1, x1, x2, so on, xn, right? So what do you get when you multiply theta transpose with x? What do you get when you multiply theta transpose with x? Theta transpose with x.
Theta naught x naught plus theta 1 x.
Equation.
This equation you will get, right? Theta naught x naught, theta 1 x1, so on, theta n xn, isn't it? Right. So which is the scalar? Theta transpose x is theta transpose is 1 by n and x value is n by 1. So 1 by n times n by 1, this is 1 by 1, which is a scalar, right? So this is what you get, right? Which is the prediction. Theta transpose x is the prediction, right? So now this is the vectorized representation of the hypothesis. A question now, right? Why is this vectorized notation is important? Vectorized notation is important, or vectorization is important, because we want to take the advantage of the parallelism, right? To take the advantage of the parallelism, we go for the vectorized implementation of this program, right? So to go for the vectorized implementation of the problem, we go for this vectorized notation, so that you can take the advantage of the parallelism exist in your computer architecture, right? So that is the reason why we go for this vectorization. All right, so this is the representation of the hypothesis in case of multivariate linear regression. And what else we need? We need a cost function. So here also we want to minimize the squared difference between actual and the predicted values. So the cost function is same, 1 by 2m sum over I equal to 1 to m s theta of xi minus yi whole square. But the representation of the hypothesis is different. There it is a line, now it is a hyperplane. And gradient descent updation rules also the same. Theta j equivalent to theta j minus alpha times the derivative of j with respect to theta j. So there j equivalent to 0, j equivalent to 1, but here j equivalent to 0 to n, right? So now a question to you. Suppose if there are 4 features, how many parameters do we have to learn? If there are 4 features, how many parameters do we have to learn?
4.
4 or 5?
5.
5.
Theta naught also there, right?
Okay.
Theta naught plus theta 1 to theta 4. So total 5. So if there are n parameters, sorry, n features, then
n plus 1 feature.
Plus one.
n plus 1 parameters we have to learn. So one more point, if you could follow, it's okay. Otherwise, don't worry about this point. But let me try to explain this. Here, there is one point mentioned here. Simultaneously update for every j equal to 0 to n. So what do we mean by that? So when you're updating theta values, you're updating this way. Theta naught equivalent to theta naught minus alpha times derivative of j with respect to theta naught, which is, let's say, something. Similarly, theta 1 equivalent to theta 1 minus alpha times something. So on theta n equivalent to theta n minus alpha times something. So here we are saying that simultaneously update all this. So what do we mean by that? When we say simultaneously update for all these things, here when you are updating for theta 1, let's say, what is the updation rule here? Look at this. Updation rule is this. Let me write it here. Theta naught equivalent to, sorry, theta I equivalent, theta j equivalent to theta j minus alpha times sum over 1 by m, sum over I equal to 1 to m, h theta of xi minus yi times xi. Isn't it the updation rule? So now look at this. What is h theta of xi? H theta of xi is theta naught plus theta 1 x1 plus theta 2 x2 plus so on theta n xn. Okay, so do you agree with me? In updation of theta 1, you have the other parameters also, theta naught, theta 1, theta 2, so on theta n. Hello? While you're updating theta 1, in this something, you have h theta of x, and h theta of x is a function of all the theta values. Hello? Isn't it that true? Isn't it true?
Yes, sir.
Overloading.
Yes.
Following or not? Please let me know so that I will modify the talk accordingly. If you couldn't follow, I'll try to teach few of the things in some other words, and we can avoid some of the things.
Taking some time, sir. It's okay.
Okay. All right, let me repeat that. See here, we are saying simultaneously update for theta j equivalent to 0 to n. It means simultaneously update theta naught, theta 1, so on theta n, right? So
Yes.
till that point it is clear. So when
Yes,
you are
sir.
updating theta j, the updation rule is this: theta j equivalent to theta j minus alpha times derivative of j with respect to theta j. This is clear, right? This rule. Okay.
Yes.
So what is the derivative of j with respect to theta j? That I have expanded here. So look at that and tell me, in this, whatever this derivative of j with respect to theta j, do we have theta naught, theta 1, theta 2, so on theta n or not? Because we have h theta of x. H theta of x is this.
Yeah.
Right. It means we have theta naught, theta 1, theta 2, so on theta n. Right. Not only theta 1, we also have the other theta values here, isn't it?
Yes,
So
right.
right. So now when you have these values, which theta naught should we consider, or which other theta values we have to consider? Is it the updated theta naught, or is it the theta naught from the previous iteration? Which one should I consider?
From previous iteration.
From the previous iteration. That's what we mean by simultaneously updating this theta naught, theta 1, theta 2, so on. Right? Because if you consider the updated theta naught, it is not possible to simultaneously update them. Right? Fine. So you have to consider the updation, the theta values from the previous iteration. Similarly, when you are updating theta n, you have to consider all the other theta naught, theta 1, so on, theta n minus 1 from the previous iteration, not the updated theta naught, theta 1, so on, theta n minus 1. Right? That's what we mean by simultaneously update for every j equivalent to 0 to n minus 1. Right? Because you're computing the gradient with respect to the previous iteration theta values. All right. So is that point clear? Simultaneously update for every j equivalent to 0 to n?
Yes, sir.
Yeah.
Yes.
So when n equal to 1, these are the updation rule. Theta naught equivalent to theta naught minus alpha times derivative of j with respect to theta naught, and theta 1 equivalent to theta 1 minus derivative of j with respect to theta 1. And when you generalize it, this is theta j equivalent to theta j minus alpha times derivative of j with respect to theta j. Alright. So remember this point, simultaneously update for theta j. Fine. So far we have discussed what is a regression problem, and then we started discussing linear regression, in which we have started with one input variable and one output variable. When you have one input variable, one output variable, we call it as a univariate linear regression. So we have discussed univariate linear regression. We have seen how to learn the optimal parameters. So what is the algorithm that we have discussed to learn the optimal parameters, theta naught and theta 1? Gradient descent
algorithm.
Descent algorithm. How do we compute the gradient with respect to one parameter? Take the derivative of the cost function with respect to that parameter. So if the gradient is positive, what are we supposed to do? Decrement or increment? Decrement the corresponding parameter. If the gradient is negative, we have to increment the corresponding parameter. We call this algorithm as the gradient descent algorithm. Then we started discussing multivariate linear regression. What is multivariate linear regression? When there are
More than one feature.
more than one feature, we call it as a multivariate linear regression. Some people call it as a multiple regression also. There is some notation confusion in the literature. So, but I don't want you to confuse by discussing all of that right now. But one point I can tell you, if there are multiple output variables, if there is more than one target variable, we call this as a multi-target regression or a multi-label regression. Multi-label regression or multi-target regression. Okay, that's we're not going to discuss, but you can repeatedly apply single target algorithm for the multiple targets. That is one of the simple extension. All right, so that is what we have discussed, and we have discussed the gradient descent updation rules for the multivariate linear regression also. Theta j equivalent to theta j minus alpha times derivative of j with respect to theta j. So this is what we have discussed so far in this section. So is that clear? Any doubts? So far, are you with me? Till the point we have discussed it so far?
Yes, sir.
Yes, sir.
Yes. Yes, are you there?
Sir, just one doubt, sir.
Yeah, ma'am, please.
Sir, linear regression means it is with only one input feature. Is that correct?
No, madam. Linear regression means it is assuming the linear relation between input and the output
We
variables.
will have a straight line. Is that correct?
Yes, line or hyperplane. Line in case of 2 dimensions. I mean, one input variable, one output variable. Hyperplane in case of multiple dimensions.
Okay, sir. When we say one input, one output variable, it is linear.
That is, when you have multiple variables, that can also be linear. When you have one input variable, one output variable, that is a line.
Okay.
Linear equation is like a line. When you have multiple input variables and one output variable, linear equation is like a hyperplane, not a line.
Okay.
So hyperplane you can imagine, right? It's like hyperplane in 3 dimension. In more than 3 dimension, it's like a cubic or something like that. Yeah.
Okay.
Cube.
Thank you.
Okay. Okay. So fine. So far good. So there are certain aspects that we need to consider when you're practically implementing this gradient descent algorithm. So one of the things that we need to take care is feature scaling. So let us try to understand what is feature scaling and why is it important. So feature scaling is bringing different features into the similar range, similar scale. That is what the feature scaling means. Like for example, if you say if you look at our example of the house price prediction, the first feature is the size of the house in square feet. That is actually in the range of, I think it's not 0 to 2000. I think in the original data set, it is around 800 to 3000 square feet. Or the range may be varying also. Maybe let's say 400 to some 3000. Okay. So this is the size of this square feet. And number of bedrooms are in the range of 1 to 5. If you observe these two features, there is a huge range difference between them. Do you agree with me? There is a huge range difference between them, isn't it?
Yes, sir.
Right. There is a huge range difference between the features. So what happens if there is a huge range difference between the features? So if there is a huge range difference between the features, when you are making a prediction, right, what is that? You have to take the linear combination of these features and predict the cost. Let's say the cost corresponding to 800 square feet is, let's say, some $400. 800 square feet and 1 bedroom. Let's say the cost corresponding to some 1200 square feet and 2 bedroom is some $500. Okay, so you have to multiply them with some variables, theta naught and theta 1 and so on, so that you will predict this cost. So when there is a huge range difference between the features, you will have to multiply these with the corresponding parameters between them. Also, there is a huge range difference, right? Because you have to make a compensation between them so that you will reduce them to this 400 or 500, map them to 400 or 500. So if there is a huge range difference between the parameters, there will be, features, there will be a huge range difference between the parameters as well. So because of that, you will have the contour graphs like thin and tall, as you see in this figure. So if there is a huge range difference between the features, your contour graphs will look thin and tall, as you see in this figure, right? So earlier, do you remember the contour graphs I have shown you was like thick concentric circles like this? Do you
Yes,
remember
sir.
this? Right. Now it's not like concentric circles, but like concentric vowels, thin and tall. Okay. So what is great deal about it? Earlier it's like a circle, now it is a vowel, right? No problem at all. We may think like that. But there is a big problem with this. If the contour graphs are like this, if there is a huge range difference between the parameters, so when you are updating the parameters, you're updating them like this: theta 1 equivalent to theta 1 minus something, theta 2 equivalent to theta 2 minus something. So in this something, you have the other parameter also theta 1. In this something, you have other parameter also theta 2. So when you have a huge range difference, suppose if this is a small value and this is a big value, what happens? You are subtracting the small value with a big value. Of course, it is a function of that, but the function of that's also a big number if this is a big number, right? So you are subtracting with this a big number. As a result, what happens? You may be subtracting it, or you are incrementing it or decrementing it more than required. That possibility is there, right? Because of the huge range differences, you may be incrementing this theta 1 or decrementing this theta 1 more than required. Hello? Possibility is there or not? If there is a huge range difference between the parameters, when you are incrementing this theta 1 or decrementing this theta 1, you may be doing it more than required. Hello? Is that possibility is there?
Yes, yes.
Right. Should I repeat or is this okay? So you take this. Let me write it, expand it here. Can you tell me two things, theta 1, theta 2? So tell me the equation for theta 1 by using this formula. Theta 1 equivalent to theta 1 minus alpha times 1 by m sum over I equal to 1 to m theta naught plus theta 1 so on, whatever, h theta of xi minus yi times xi. Okay, so this xi we have theta 2 also, right? Theta naught, theta 1, theta 2, theta 3, all that is there in that x. Similarly, theta 2 equivalent to theta 2 minus alpha times 1 by m sum over I equal to 1 to m h theta of xi minus yi xi. So this we have theta 1 also here. Okay, so suppose if theta 2 is a big number, theta 1 is a small number. So when you're taking this function, when you're computing this function, because theta 2 is a big value, there is a chance of this this quantity to be a very big possibility is there. You will get a big number here. This is a big number and this is a small number. What happens when you subtract small number with a very big number? You'll be decrementing it more than required. Am I right?
Yes, sir.
Or similarly, when you are incrementing it, when you are adding something, if this is a big negative number, negative of negative is positive, then you are incrementing it more than required. So as a result, what happens here? You are incrementing it more than required, decrementing it more than required, incrementing it more than required, decrementing it more than required. As a result, your path to reach to this optimal point is zigzag. Okay, so if you want to visualize it in terms of the cost function, your cost function looks like something like this. Let's say this is theta1. Okay, so you started with somewhere here. Let's say you are incrementing it more than required. It means you're crossing the optimal point. Let's say that you started here, somewhere here. Okay, incrementing it more than required. So it means you're crossing the optimal point, reaching there, realizing, oh no, I have already crossed the optimal point. Now I have to go back, decrementing it more than required. Now it's coming here. It is decrementing it more than required, incrementing it more than required, decrementing it more than required, incrementing it more than required, decrementing. As a result, your path to the reach to the optimal point is becoming zigzag, right? So you're taking this zigzag path to reach to the optimal point, something like this. Okay. So if this is the source A, this is the destination B, which path would you prefer? The zigzag path or the straight path? Which path would you prefer? We
Straight.
prefer the straight path. Why we prefer the straight path? Because it is faster, right? We can go more quickly to the destination if you follow the straight path. Whereas if you take the zigzag path, it takes more time to go to the optimal point. So what happens if there is a huge range difference between the features? The contour graphs will become thin and tall. As a result, it will become when you're updating these parameters, you may be incrementing them or decrementing them more than required. As a result, your path to reach to the optimal point is becoming zigzag. Okay, so what is the solution for this? You have to bring them to the similar ranges, right? So to bring them to the similar ranges, we follow this feature scaling approach, or normalization also we call them. We call it as a normalization also. There are various popular techniques. There are various methods. Some of the popular techniques I have mentioned here: max min scaling, mean normalization, z-score scaling. Simple scaling, you can say, divided by the maximum value of the column. Divide every value by maximum value of that column. Then that will bring the values in the range of 0 to 1. Okay, that is one simple feature scaling technique. So mean normalization, what it does is that subtract the mean value of that column, divided by the standard deviation. This is what the mean normalization is doing, right? So all right, so that is about the feature scaling. So have you understood what is feature scaling and what is the importance of it? Why we have to do feature scaling? These 2 points.
Clear, sir.
Clear. Okay. Fine. The next point that we need to take care when you're practically implementing this gradient descent algorithm is learning rate alpha. Learning rate alpha we have to take care of. So which is the step size we call it as. So how to choose this step size alpha? So we have to ensure that a gradient descent algorithm is working. In order to ensure that the gradient descent algorithm is working, when do you say that the gradient descent algorithm is working? If it is working for objective, then we can say that the gradient descent algorithm is working. And what is our objective? Our objective is to minimize the loss or minimize the cost. It means when you plot this j of theta or the cost function versus the number of iterations, it should be gradually decreasing like this. Suppose if it is increasing, if the cost is increasing over the number of iterations, so can you say that the gradient descent algorithm is working? Can you say? Can you say the gradient descent algorithm is working if the cost is increasing over the number of iterations? We can't
No,
say
sir.
that, right? Right, because it is not working for our objective. Our objective is to minimize the cost. If the cost is increasing, then how can we say that gradient descent algorithm is working? It means there is something wrong. If the cost is increasing, there is something wrong. Probably you need to adjust alpha value to the smaller values. You need to take the smaller values, right? So why is that? If the cost is increasing, we have to take the smaller values. Why is that? If the cost is increasing, we have to take the smaller value is the question. All right. Let me take this one example. So imagine that there are two beautiful hills. Okay, imagine there are two beautiful hills, something like this, two beautiful hills, and there is a valley point in between the beautiful hills. There is one village in between these two beautiful hills, and you have got house there. So your house is located here at a beautiful location of the valley point between the two hills. Okay, so let's say you are somewhere here, and imagine you are a very big Rakshasa like Kumbhakarna, right? It means you have got a very lengthy leg. So one step you are taking, it means you're going from, you're going from this hill to the other hill. Okay, this hill to the other hill. And if you was taking one step back, you're coming from that hill to this hill. If you're taking another step, you're going to this hill, right? Will you be able to reach your home?
No, sir.
No, even if you're able to reach your home, it may take a very longer step because you're moving front and back between the hills. Going front, coming back, going front, coming back. So your path to reach to the optimal point is zigzag. To your home is zigzag, right? Because of this large step length that you have. So if the step size is bigger, it means you're crossing the optimal point. So do we have the need to adjust this alpha value or not? If the cost is increasing. So when the cost is increasing, when you're crossing the optimal point only, the cost is increasing. Power has gone. So please let me know if I get disconnected in between. I'll connect to the mobile. I hope I'm audible for now because of the CPS backup. Am I audible?
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir. So now, yeah, you're crossing the optimal point, and because of that, because you're crossing the optimal point, that is why the cost is increasing. Why you're crossing the optimal point? Because the step size is bigger. That is why you're crossing the optimal point. So it means if the cost is increasing, probably you need to choose smaller values for alpha so that you will not cross the optimal point. That's the reason why we need to choose the smaller values when the cost is increasing, right? So imagine you're a small ant here. It means you are taking the tiny steps. You're going like that. Small steps. Small steps. Will you be able to reach your home?
Oh, long time.
It takes a very longer time, but definitely you'll be able to reach your home, right? Right. There is no uncertainty, but definitely you'll be able to reach your home, but it takes a very longer time. So choosing the right value for alpha is very much important. Even if you choose this very small value, that is a problem. It takes a very longer time to converge. Even if you take a very bigger value for alpha, that is also a problem because you're crossing the optimal point and taking the zigzag path. That is why that is also taking a longer time, and there is no guarantee that you will reach to the optimal point also, right? That is the problem with this alpha, that you have to choose the right value for alpha. Now the question is how to choose the right value. There are multiple ways. This is a hyperparameter kind of thing for this model. Alpha is a kind of hyperparameter. It means you have to tune this hyperparameter by trying multiple values and find out the validation error with respect to the validation data set. So whichever alpha value, minimizing the validation error, you choose that alpha value, right? So that is one way of choosing this alpha value, right? By hyperparameter tuning. There are few more algorithms. They call them as the line search algorithms. There is another algorithm also. I always forget that name. But anyhow, you search for the line search algorithms, you'll be able to find.
So grid search is also one algorithm to
Grid search
perform
is for
fine
the
tuning.
grid search is for the that hyperparameter tuning, madam. One of the model for the hyperparameter tuning. But
Okay.
I'm not talking about that. The line search
Sorry.
algorithms. Yeah, no problem, ma'am.
Yes.
It's good that you have mentioned one algorithm so that everybody also got that idea, right? How to perform. Yeah, one of
But it
the
is basically used for deep learning models.
not only deep learning, any of the models you can use the grid search algorithm. Basically, it tries the various combinations of the hyperparameters and look for the combination that works best. Okay, that's the idea behind that. So that can be for any model, not necessarily for the deep learning model. Yes, but in deep learning models, nowadays people are using it. That's why you might have come to know about it. Yes. So the line search algorithm concept is they dynamically adjust the alpha value. It means they start with a very big value alpha. As they're approaching towards this optimal point, through some estimation, they estimate that how far we are to the optimal point. As they're approaching close to the optimal point, they reduce the value for alpha. So initially it may be taking bigger steps. As they approach towards the optimal point, they reduce the step size and take small steps. So they dynamically adjust the alpha value. This is the line search algorithms. Okay, this is different from the grid search. Grid search will be trying multiple combinations of the hyperparameters and select the combination that work best with respect to the validation error. All right, so that is different. That is kind of hyperparameter tuning. But this is not hyperparameter. It is a dynamically adjusting alpha value and reaching to the optimal point. So that's why it is saving a lot of time as well. Okay, is that clear? How to select the optimal value
Yes.
for alpha and what is the importance of it. Okay, fine. So now we'll go to the vectorized notation. Vectorized notation of this problem. So I already told you why vectorized notation is important. It is to take the advantage of the parallelism. All right. So if you remember, the model was like this: theta naught plus theta 1 x1 plus theta 2 x2 plus so on theta n xn, something like this. So now, if to generalize this, we have taken x naught equivalent to 1. So you can add another feature here, which is a vector of 1s, x naught. In addition to these features, you can add another feature, which is a vector of 1s. Okay. So now, to get, if I take theta as one vector, theta is a one vector, right? Theta is one vector, theta naught, theta 1, so on, theta n. Okay, so and this is one of the instance, right? X naught, x1, x2, so on, xn, which is x naught 1 1 1 1. Superscript 1 means it is instance 1. Superscript 2 means it is instance 2. All right. So what should I do in order to get this value, this equation? Is it okay if I multiply this n by 1? So this is what? N by 1. This is 1 by n. Is it okay if I multiply this 1 by n with n by 1? Hello? To get this. Is that okay? Will I get the same? I will get the same, right? Right.
Yes, sir.
Similarly, in order to get the prediction for the second instance, I multiply the second row with the same theta and third row with the same data, same theta, and so forth. So this is kind of x that I am taking here, x. Can you tell me the size of it if there are m instances? If there are m instances and n features, what is the size of it?
M
M
plus
cross n plus 1, because
M
there
plus
is one additional column we have added here, right? So m cross n plus 1, right? And what is the size of this? Size of this? This is n plus 1 by 1, right? So if I take this x, this as a x, this as a x, this as a x, and this as a y is the vector of all the ground truth labels or the actual labels, right? So this is x, which is of size m by n plus 1. This is of size m by 1. Now the task is to learn theta such that when you multiply this theta with x multiplied by theta, what is the resulting matrix size? M by n plus 1 and n plus 1 by 1. What is the resultant one? M by 1, isn't it? Hello? Could you
Yes,
follow?
sir.
Right. So this is the prediction vector and this is the actual vector. So the task is to learn theta such that x times theta is equivalent to y.
Wait.
So this is what is the problem is, right? So now can you recall this cost function that we are trying to minimize? What was the cost function? 1 by 2m sum over I equal to 1 to m x theta of xi yi whole square, right? So how to vectorize this implementation? implementation of the cost function. How to do that? So can I say x times theta is equivalent to h theta of x, which is the prediction vector? Can I say this?
Yes.
Right. And y is the actual vector, right? So now h theta of xi, capital X, this is of size m by 1, y is also size m by 1. What you are essentially doing, you're taking the difference between them, right? So I'm taking the square of it, right? Hello, can you please mute yourself if you're not speaking? It's creating a disturbance. I don't know from where it is coming, but yeah, some disturbance is coming. Fine. Yeah. So now, please tell me, please answer, please unmute yourself and answer. So can I write this as 1 by 2m sum over I equal to 1 to m ei squared if I say ei is h theta of xi minus yi?
Yes, sir.
Ei squared, right? So how can I get ei's errors? By subtracting this h theta of xi minus yi, I will get all the errors e1, e2, so on, em. Correct? H theta of xi minus yi. So this is a vector, this is a vector. So when I subtract, I will get all the errors or not?
Yes, sir.
Right. All the errors, let us call that as a E. So what happens when I take E transpose with E? E transpose with E?
Squares.
E1.
E transpose with E, what will I get? E1 square plus E2 square plus E3 square plus so on EM square. Am I right? Hello? Am I right? E transpose is E1, E2 row vector and E is the column vector. What will happen when I multiply this? Oh God, what happened? Where is this slide that I'm speaking? Yes, yeah. Yeah. So what will I get? I will get this. Isn't it sum over I equal to 1 to m ei square?
Yes, sir.
So if I take E transpose times E, this is a vectorized implementation of this. And what is E? E is h theta of x minus y whole transpose times h theta of x minus y. Agree? So let me write it this way. Confusing, or should I repeat or following what it is?
So E is the prediction minus the actual value.
Prediction minus actual for in a vectorized. So this is 1 by 2m x theta minus y. X theta is the prediction, y is the actual value, transpose x theta minus y. So this is like E transpose times E.
Not getting properly, sir.
Not following properly. Should I repeat? Santosh sir, should I repeat? Not audible.
Now it's clear. Now it's clear, sir.
Clear.
Now
Clear.
it's clear, sir.
Okay, fine. Fine. So shall I move on? Is this clear? Vectorized implementation of the cost function? Madams?
Yes, sir. Yes, sir.
Yeah.
Sir, please explain this last one. This
Last one?
this J equation.
J equation. Okay. So do you understand this E transpose times E, madam? Error.
Yes, sir.
So what is error? I said the difference between the prediction and the actual value, right? So what is the prediction? H theta of x minus y, right? What is h theta of x? Which is x times theta only, right? X times theta minus y. So E transpose means x times theta minus y transpose, and E transpose times E, which is x theta minus y. Clear, ma'am?
Yes, sir.
Yeah. So shall we move on? Any other query you can ask? Rishali madam, it is clear to you, right?
Yes, sir.
Yeah.
So one doubt is that
square
only we are splitting it like this, sir.
Yes. That is just, this is a vectorized implementation of the same thing. Instead of writing a loop, if you have to write sum over I equal to 1 to n, what will you write for I equal to 1 to n? x theta of xi minus yi sum equal to sum plus s theta of xi minus yi whole square. This is what you write, right? But instead you can write a single statement and implement this, and this is much faster as compared to writing loop.
That's
That's
what
the
the
difference.
x theta minus y is a vector that you
Uh,
are writing it in the transpose and multiplying it.
Yes.
Okay. Sir.
And similarly, updation rules also you can vectorize. You can update the whole theta at a time instead of writing loop like this. This is the vectorized updation rule. Okay, you can work it out and you will see that you will get the same thing when you expand this. Okay, so this is about the vectorization. So far in this session, we have discussed what is the regression problem and what is univariate linear regression, what is multivariate linear regression, how to learn this optimal parameters in both the cases, and we have also seen the vectorized implementation of them, and we have also seen some of the suggestions while implementing, that is feature scaling, as well as how to choose the optimal, right alpha value, right? So these are the things that we have covered. So is all these points clear so far, whatever that we have discussed?
Yes, sir.
Yeah.
Yes,
So
sir.
now we'll look at the closed form solution, which is another kind of solution other than the gradient descent algorithm. Okay, so closed form solution is like, it is providing the solution through the linear algebraic equations. Providing the solution through linear algebraic equations. Let us recall the problem. Let me go back to the previous slide. So you see that here is the problem. We have given x and y. The task is to choose theta such that x times theta is equivalent to y. Agree? X times theta is the prediction, y is the actual value. Right? Predicted values, actual values. So the task is to choose theta such that x times theta is equivalent to y. Am I right? Agree, all of you?
Yes, sir.
Right. So now we want to choose theta such that y equivalent to x theta. So it means y equivalent to x theta. So can I multiply it with x inverse both the sides? X inverse y is equivalent to x inverse times x times theta. I can do that, right? So tell me, A inverse times A. What is this? Identity matrix.
Matrix.
Right. So x inverse x is the identity matrix. Right. So using equation 1, I can write this. So now anything multiplied by identity matrix is equivalent to that matrix, right? Right.
Yes.
So using equation 2, I can write it as a theta. Equation 2. So x inverse y is equivalent to theta. We know what is x, we know what is y. Substitute, you will get theta. But what is the problem here? Problem here is that x may not be a inversible matrix all the time. X may not be a inversible matrix all the time because x is a not square matrix itself, right? So this may not be a inversible matrix. So to address this problem, let us expand it further. So can I write y is equivalent to some identity matrix times y instead of y using equation 2? Can I write this? Hello? Can I write this?
Yes, sir.
Can write this, right? A equivalent to I times A. So y equivalent to I times y. I can write this. So now, can I expand I as x transpose inverse times x transpose?
Yes, sir.
Using equation 1?
Yes, sir.
Because identity matrix is equivalent to A inverse A. I call A equivalent to x transpose. Right? Using equation 1, I can write this. So what is B inverse times A inverse? Can it be AB whole inverse?
Yes.
B inverse times A inverse. Using that,
Yes.
I can write this as a x transpose x whole inverse times x transpose times y is equivalent to theta. X transpose x is always a square matrix. There is always inverse exist for that, right? There is always inverse exist for this. So it is inversible matrix. So theta equivalent to x transpose x whole inverse times x transpose times y. Because this is an inversible matrix, it is feasible, right? Fine. So now, fine. This is using the linear algebraic equation. We can solve for theta. You know x, you know y. Substitute in that equation, you will get theta. Very simple. Now, question coming in here. If you can solve theta using a simple equation like this, Why is that you have to bother about gradient descent algorithm? Why to iterate it over many iterations, adjust the theta values, adjust the alpha value? Why all such headache? Just substitute x and y values in the equation and you will get the theta value directly. Why do you have to bother about all such things? Right, which is a big headache for us. Choosing the optimal value for alpha, choosing the optimal values for theta, iterate it over multiple iterations. Why is this a big headache? There is the equation, substitute in this equation, you know x, you know y, substitute in the equation, you'll directly get theta, optimal theta. Did you get this down? At least after I said that, are you feeling it?
Yes, sir.
Okay. So the problem with this is that there is the inverse operation in this equation. And the complexity of the inverse is order of n cube. Okay. So this is okay when n value is small like 1000 or 10,000. What if n value is big, very big, like 1 lakh, 2 lakh, like that? Then order of n cube is too much. It takes a very longer time, right? So only reason is time. Okay. So the gradient descent algorithm works much faster as compared to this closed form solution when n value is big. Okay, and closed form solution is better when the input size is smaller. No need to choose alpha, no need to iterate, nothing. You can directly get the theta values. Okay, so that is about the closed form solution. So is that clear? Closed form solution, and what are the pros and cons of the closed form solution? Clear, right?
Yes,
Yes, sir.
Yes, yes. All right. So we have discussed one of the optimization algorithm, which is the gradient descent algorithm. We also call it as a batch gradient descent algorithm, in which while updating one parameter, we consider the gradient with respect to all the examples. So if you remember, the updation rule is theta j equivalent to theta j minus alpha times the derivative of j with respect to theta j. When you're computing this gradient, you're computing with respect to each and every example. 1 by m sum over I equal to 1 to m, and this is the gradient part with respect to each and every example, right? So it means you're computing the gradient with respect to each and every example, right? So then average of all the gradients you are taking and using that for the updation, right? Suppose if you consider only one example at a time, it means compute the gradient with respect to only one example at a time, like this as it is shown here, and repeat it over all the examples. It means you're frequently updating theta with respect to each and every example and repeating it over all the examples. Then we call it as a stochastic gradient descent algorithm, right? So here the problem is that problem with this is that you may have to wait a longer time for a single updation, but problem is this is that it may be highly unstable, like you may get zigzag things because of the frequent updation that you are getting. So mini batch gradient descent is something in between both of this gradient descent and stochastic gradient descent. In the gradient descent, we are considering all the examples to update a single parameter, whereas in case of stochastic gradient descent, only one example at a time, repeating it over all the example. So in case of mini batch, you're dividing this data set into multiple mini batches. Let's say there are 100 instances. You can divide it into 10 mini batches, each mini batch size of 10 size. Okay, 10, 10 like that, 10 mini batches. And you update the gradient with respect to one mini batch at a time and repeat it over all the mini batches, right? So this is in between, this takes the advantage of both the gradient descent algorithm as well as the stochastic gradient descent algorithm. So this we call it as a mini batch gradient descent algorithm. I hope that is clear. Is that clear? Shall we move on?
Yes.
Okay. So now we look at the probabilistic interpretation of the linear regression. Unless you pay attention, it is slightly difficult for you to understand, for some of you to understand. Okay. So either you pay attention or don't worry about this. Okay. Two of these things you do, right? One of these two things you do, right? So yeah, better pay attention. If you couldn't follow also, don't worry. As long as you understand the intuition behind the cost function, how to update that, all that is fine. Okay. But if you understand the theoretical view of it also, it is better for you to develop such algorithms in future, right? So if you just want to apply, so far whatever the knowledge that you have gained is okay. Okay. if you want to propose some algorithms like this in future in your domain, then it is required to understand the theoretical view of it also. Okay, fine. Okay, so pay attention, I'm saying. So a question to you, first of all, before we move to this, a question to you. How many slides? Okay, 3 slides. I also need to go to hospital after this. Okay, fine. Let us try to complete within 10 minutes. So fine. All right. So this is the data set, let's say, and you want to fit a line for this data set. What was the assumption? Assumption was there exists a line that fits for the data. It means there exists a linear relation between output and the input variables. It means the pattern can be captured through a line. Okay, that's what the assumption, right, of the linear regression model. Agree, all of you?
Yes, sir.
Yeah. So now a question to you: is it possible to fit a line so that error is 0 for all the instances?
No.
No, it is not possible.
Any line that you fit, for some of the instances the error is high. Am I right? What all that you're trying to do is to minimize the error. It means for most of the instances the error is either 0 or very small. Isn't it?
Yes.
That's what we wanted, right? Right. It means what? There is some noise in the data. I mean, according to the assumption, you're saying that the data, you can fit a line for the data, but it is not possible to fit a line to fix all the points. It means there is some noise. It means the points are deviating here and there from the line, right? It means there is some noise in the data. It means the output y is equivalent to some function h theta of x plus some noise. This h theta of x is the line equation, theta naught plus theta 1 x, right? So now the assumption is that noise follows the Gaussian distribution, in a sense that, what do we mean by the noise follows the Gaussian distribution? When you're trying to fit a line, how do you want to fit? You want to fit a line in such a way that for most of the instances the error is 0, or very few instances the error is 0. How do you want to fit it? How do you want to fit it?
Most instances.
For most of the instances the error is 0. It means
Yes.
the density distribution of the errors is high at this line with a mean 0, right? So you want to
Yes.
fit this line so that most of the instances come at a 0 error with a mean 0, and very few instances are maybe with high error, right? So it means as you move this side or that side of the line, the error is small. I mean, the error, number of instances that are falling there must be less, right? The frequency distribution of them must be less. It means you're assuming that the noise following the Gaussian distribution. Till this it is clear why the noise should follow the Gaussian distribution, why the assumption is clear, right? You want the most of the instances the error is 0. It means all of with a mean 0 and variance 1, it follows the Gaussian distribution, right? So here M is the noise, Gaussian noise with a mean 0 and variance is 1. Variance 1 means constant variance, constant spread, right? That's what the assumption is, right? So it means we are assuming that y is equivalent to h theta of x plus m. M is the Gaussian noise with a mean 0 and variance 1. Now what is your problem? Your problem is you have given x1, y1, x2, y2, so on, xm, ym. Okay, now you're saying y is equivalent to x theta of x plus m. So it means yi is equivalent to h theta of xi plus some Gaussian noise mi. Right. So instead of yi, can I write this and formulate the problem like this? X1 h theta of x1 plus m1, x2 comma h theta of x2 plus m2, xm comma x theta of xm comma mm. Can I say that? Hello?
Yes.
Everybody. If
Yes,
you
sir.
couldn't follow, please let me
Yes,
know.
sir.
Yes,
Yes,
I can say that. Now here, what is this m1, m2, so on, mm? These are the Gaussian random variables, and the assumption is that they are independent of one another and they are coming from the same distribution, Gaussian distribution. It means they are distributed in a IID fashion. IID fashion means independently and identically distributed. independent and identical. Identical because all of them are coming from the same distribution, and independent because the noise in one example is independent of the noise in the another example, right? So they are independently and identically distributed. So do you remember the Gaussian distribution formula? If any variable z with a mean mu and variable variance sigma square, then it has the following probability density function. This is the Gaussian distribution formula that I hope you remember this, because yesterday only we have discussed this, right? So now what we are saying, m is a Gaussian variable with a mean equal to 0 and variance equal to 1. Can I substitute and get the probability density function for m? Can I substitute and get the probability density function for m? I can
Yes.
get that, right? So substitute mu equal to 0 and sigma equivalent to 1. You will get this. Okay. So we're saying that yi is equivalent to h theta of xi plus mi. Right? So here m we have. So can I write mi is equivalent to yi minus h theta of xi? By bringing this here, this side?
Yes.
Yes.
So can I substitute mi equivalent to this and get the Gaussian, get this formula for variable y? I'm substituting that, right? So 1 by square root 2 pi e to the power minus of y minus h theta of x whole square by 2, right? So it means if you want to estimate the likelihood of a one particular instance yi, this is the likelihood estimation for one particular instance in the data set, yi minus h theta of xi whole square by 2. This is the likelihood estimation for one instance, right? For one instance xi yi. Okay. So what if you want to estimate the likelihood of the data? What is the data? Data is a set of all the instances x1, y1, x2, y2, so on, xn, yn. Okay, right. So let us call it as a z, z1, z2, so on, zn. Zi is a pair of xi and yi. Okay, or you can just call it as a y1, y2, so on, yn to avoid confusion. y1, y2, so on, yn. And this is the likelihood estimation of one instance yi. So if you want to get the joint probability, it means the likelihood estimation of the data, you get the joint probability of y1, y2, so on, yn. What is the joint probability if the variables are independent of one another? What is the joint probability if the variables are independent of one another? Isn't it the product of the individual probabilities? Probability
Yes.
of y1, probability of y2, so on, probability of yn. Okay, and you know what is the probability of yi, which is this. So substitute, right? So the task is to find out a theta that maximizes the likelihood of the data. The task is to find out theta that maximizes the likelihood of the data. How do you estimate the likelihood of the data? It is the product over the likelihood of the individual instance likelihood. So product over I equal to 1 to m, this is the likelihood of the individual instance that we have got here. Clear? Are you following so far?
Yes, sir.
Yes. So the task is to find out theta that maximizes the likelihood of the data. It means you need to choose theta that maximizes this. Product over I equal to 1 to m, sum over all product over I equal to 1 to m and this term, right? So this is what is the task. The task is to find out theta that maximizes the likelihood of the data. Tell me one thing here. I tell you something, ask a true or false question. Just tell whether it is true or false. Maximizing f of x is equivalent to maximizing f of x by 2. Yes or no?
Yes.
Yes, because they are proportional to one another. This we have seen also already.
Yes.
Maximizing f of x is equivalent to maximizing f of x whole square. True or false?
True. Yes.
True. Maximizing f of x is equivalent to minimizing minus f of x. Maximizing f of x is equivalent to minimizing minus f of x.
True, sir.
True, because they are inversely proportional to one another. Maximizing f of x is equivalent to minimizing 1 by f of x. True. Maximizing f of x is equivalent to maximizing log of f of x.
True.
True. They're proportional to one another. I said true or false question, but I've asked all the true, only true questions. Okay. So maximizing f of x is equivalent to maximizing log of f of x. Agree, all of you?
Yes.
Right. So can I say maximizing this is equivalent to maximizing log of this?
Yes.
I can say that, right? So,
Yes.
so take the log here, log here. What happens when you take log of a times b? Expand this, what will you get?
Log A
Log
plus
A
log
plus log
B.
B.
Log b. So this is a product over. What happens when you expand? It will become sum over, isn't it? Sum over log of all these individual things. Am I right? So when you expand this, you got log of 1 by 2 pi, and this e and log will get cancelled. You will get sum over I equal to 1 to I, yi minus h theta of xi by 2 whole square. So the task, got it, getting it right? Or should I elaborate the whole thing?
Once more, sir.
Yeah, yes, let me write. As 1, 2 steps I skipped, that's why you're not following. Let me write those 2 steps. Let us write the formula first. Log of a times b is equivalent to log a plus log b. Now I'm expanding this. Log of product over I equal to 1 to m 1 by square root 2 pi e to the power minus yi minus h theta of xi whole square by 2. When you expand this, you will get log of 1 by square root 2 pi plus log of base e to the power minus y1 minus h theta of x1 whole square by 2 plus log e to the power minus y2 minus h theta of x2 minus whole square divided by 2, and so on. Agree? So far till m, sorry. Right. So this log a base e, both of them will get cancelled, right? You will just y1 minus h theta of x1 whole square. So can I write it this way? Log 1 by square root 2 pi minus of sum over I equal to 1 to m yi minus h theta of xi whole square by 2. I can write it this, right? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Right, and this is a constant term, so maximizing this is equivalent to maximizing just this. This is as it is a constant, right? So I just want to find out theta that maximizes this. Okay, maximizes this. Okay, as it is a constant, I'm ignoring this. So maximizing minus of f of x is equivalent to minimizing plus f of x. Hello?
True, sir.
True. Right. So instead of minus, can I take plus here as a minimization function?
Yes,
So
sir.
minimizing. So find out theta that minimizes this. What is it? Isn't it the squared loss? Isn't it the squared loss?
Yes.
That's the reason why we are using this squared loss. Okay. So there are some assumptions we made about the data. Based on that assumptions, we arrived at this squared loss. Okay. So why is this probabilistic interpretation important? So if you really understand it, no, you will appreciate it very much. Okay. I hope you understood. It means I hope you will appreciate it.
Yes, sir.
Yeah. Why is this important? Because we are getting the squared loss based on some assumptions made about the data. We made that assumption that noise is additive and noise follows the Gaussian distribution. What if the assumptions are different? You would have ended up with a different loss function. Am I right? So that is why it is important to understand this theoretical view, because it is based on some assumptions. If the assumption changes, then your loss function will change. That is why it is very much important to understand this probabilistic interpretation of the loss function. All right. So that's all for today. If you have any queries, I can take. Otherwise, we can wind up the session and continue it in the next class. I hope everything it is clear and you have enjoyed the session.
Yes, sir. It was
Very
clear.
clear.
Yeah. So, all right. So thank you very much then. I will share the recording also, and slides Annie have already shared with you. Okay.